Okay, so we are going to be looking at our next module, which is Module 4, Gear Kinematics Analysis and Selection. So as we look here, you're going to notice the same type of format that we've seen previously. Our learning plan is going to contain the PowerPoint presentations that we'll be looking at. I have a part 1 and a part 2, okay? And then you're going to notice that we're going to have our familiar things to hand in, which are going to be the practice problems and the assignment. Session recordings, if we click out there, you're going to notice that I will be populating with what we're going to be doing today and the next time that we meet. But I do have the previous year's session recordings out here if you're interested. Really very similar information, the same information, but just from a previous year. I kind of keep those out there in case anybody, for instance, wants to work ahead, or if they know that they're not going to be around and they're anticipating an absence, or in the event that for some reason my recording doesn't work, I like to have those out there so I can maybe refer to the previous year if needed. So anyway, so those are out there for you. And then I did want to peek really quickly at our practice problems and our assignment. The practice problems that we're going to be handing in for Module 4 are going to be the following examples. This is what my PowerPoint presentation with the examples that we're going to be going over. I want to make sure that you're actively following along, doing these with me, because we are going to be doing those in the fashion that I'm expecting your homework to be handed in. So that kind of gives you that practice as well as some formatting that you can, make sure that you understand before you hand in your assignment, which is assignment number 4. Quite a few problems here, okay? I will tell you, when we looked at velocity analysis, that was there was a lot of steps to that. Okay, there was some CAN calculations, there was AutoCAD, and I don't know if I said it or not, but that I feel is as complicated as the problems get. We kind of now move back into kind of working problems by hand. So you'll notice that we have quite a few that we're going to be looking at, but they aren't going to have additional, like if you would, layout work associated with them. It's going to primarily be calculations and working out for things that are unknown. So, so through our example problems, we'll be preparing you for those. You'll also notice that I do have an answer key here, like you've been seeing in previous assignments. I have the final answers here. My expectation on the assignments is always that you're checking your work to this so that you know how you're doing. I realize that as you're working, especially independently, if I'm not available to answer questions, sometimes you don't know, hopefully I did that right. Hopefully, you don't really know. So having that final that final answer as just kind of that confirmation that you're doing okay, gives you that confidence to move on to the next step. But with that, my expectation is that you're taking a look at that before you hand in. And then I would like to, address any issues. If you have any questions, like I'm not getting that final answer, that's what our lab time and, when I ask, do you have any questions, is for. Okay, so make sure that you're taking a peek at that. It's not, I'm going to say this, it's not for me to, get easier to, it's easier for me to correct. It is in a sense, but yet I feel like I get better quality work when you guys do take that extra step, because then if something didn't match, you go back and you troubleshoot and you kind of figure it out. There's learning that occurs there. So I think that's really important. Okay, so any questions right now in terms of our normal stuff? Okay. There is one extra fun resource here, and we'll kind of look at that at the end, but it's just a little link to a site that has some gear related things. So let's take a look at our learning plan. And what I'm going to do is I'm going to open up our PowerPoint presentation, part 1, or lecture number 1. And again, like I said earlier, we're going to be looking at chapter 10 in our book. This is the gear chapter, if you would. Yes, we're kind of skipping around in the book a little bit. We're not covering each and every chapter, but the ones that are most important, and this is one of the important ones. So the objectives of this chapter are going to be kind of giving you a look at like different types of popularly used gears out in industrial applications. And we're going to be settling on and focusing specifically on the spur gear. I want you to be able to calculate center distances. That's really important because that is going to help us with the spatial relationships that we end up seeing, especially layout-wise, in the work that we do. And then calculating velocity ratios and trains. Well, that'll make a little bit more sense as we get into things. So the function of a gear is to transmit motion from one rotating shaft to another. Now, many times we're going to be either increasing or decreasing the speed. Sometimes it can be keeping the speed exactly the same, but that means it would be changing direction. So increasing or decreasing that speed of the rotating shafts. We can change the direction, meaning clockwise, counterclockwise, because these are things that are rotating about a fixed center. For that motion. And it's also going to have to do with increasing or decreasing torque. We are not going to be specifically talking about torque in kinematics because torque requires us to calculate forces. And as we know, in kinematics, we are just interested in motion and like your space that you're going to be taking up. Okay, so it's layout work, I like to say. So we will deal with forces and torque and really kind of finishing up a gear problem by specifying gears in our design for machine elements class when that comes up for you guys in the spring. Okay, so you'll kind of add to the work that we're doing here. Now, many times, and there's some type of a drive that gears are going to be mounted to, and probably the most popular application of a gear drive, if you would, is going to be reducing the speed of rotation coming off of a motor. A motor a lot of times is going to have a fast speed. So for instance, 1750 RPMs, 1100 RPMs, 900 RPMs. It's kind of fast for especially operations where we need to do some work and maybe even have some large torques that we have to deal with. So in order to accomplish that, we need to reduce that speed so that it's something that's more workable, and we want to increase the torque. A kind of a classic example that I bring up, and I think we see something very similar in an example that we're going to be looking at, is the grocery store conveyor. Okay, when we have a grocery store conveyor, underneath, the conveyor belt itself, there is, kind of a drive that's going on, and it's going to be driven by the input speed off of a motor. Now, if you can imagine, if we had a motor, even if it's, let's say, 900 RPMs, that's going to actually move a conveyor belt very fast. So if we would put something, on our conveyor belt at the grocery store, it would like fly, to the end. And that probably isn't exactly how we want that to go. Additionally, many times when we do have those high speeds, there isn't much torque that's created. Okay. So in that case, we don't have the ability to do as much work. So for instance, if you set your a case or two of water on the conveyor belt, if it would be going at a high speed with low torque, now all of a sudden you kind of like stall that conveyor out and it's not going to move. Okay. And that's again another situation that we don't want and in the grocery line. So you have to appropriately specify, and either we sometimes say gear down or reduce the speeds, increase the torques so that we can properly do the work that we need to at the speeds and such that are expected. So the first thing we're going to look at in our chapter here is going to be on page 261, and we're going to look at a couple different types of gears that you may or may not have come across or have seen, but they're out there for industrial applications. So on page 261 here, okay, we've got a number of different types of gears in figure 10.3. So starting at the top here, we have spur gears. Spur gears are the most important type that we see used in an industrial fashion. They're also going to be the ones that we're going to focus on in this chapter, as well as, going forward. The reason we do spur gears is for a couple of reasons. Number one, all of the relationships with gears hold true no matter the type of gear that we're dealing with, okay? It's just that some equations and sizing are going to be a little bit different, or orientation of the gears is going to be a little bit different. So we get a lot of mileage out of that. Secondly, and I'm not using this and saying that it's a bad thing, but we don't have unlimited amount of time to get through this material. I would love to go through and do problems with all the different types of gears because you'll probably see them. But we want to get you familiar with, number one, the most popular type, and number two, the applications that can cross over, or the relationships that can cross over, because we simply just don't have the time to get through them all. Okay. So I assure you, even though we're going to be focusing just on spur gears, it's the most appropriate, most widely used, as well as the relationships are going to continue to cross over. The other type that we see here, and really in spur gear fashion, is a rack and pinion. And really the only difference here, as you can see between the two, is when we have a set of gears in terms of this gear set, we've got two rotating shafts, okay? When we have a rack and pinion, we've got one rotating shaft, and then we have linear motion, because if you would, the rack is laid flat horizontally in this case, and now you just travel back and forth on it. It's kind of like taking the outside of the gear and kind of cutting it like a ribbon and then laying it flat, okay, and then running back and forth. So that's another arrangement that can be accomplished with gears. The next types that we see here are going to be an internal gear. This is where we run what we call our pinion. The pinion is always going to be the smaller of the gears that are in relationship with one another or in mesh with one another. So the smaller gear is called the pinion. The larger gear is just called the gear. Okay, gear and pinion. So in this case, our pinion is going to be have its traditional layout, if you would, with the teeth on the outside, but our gear has internal teeth, so it's on the inside. So it's a little bit different relationship, but again, the same equations hold true. The next one that we see here is a helical gear set. Now, in this case, you're going to see that the helical gear set, now sometimes people call them helical, kind of the same thing, I believe. My husband says helical. He corrected me. I said, I think it's helical. What do you guys think? Anybody have any experience with helical or helical gears? Helical. Shoots. He might be right. Dang it. I'm not going to tell him though. I think it's helical. Okay. Well, I'm going to say helical today in class. So, so you'll notice here that they have a little bit different tooth pattern across what we call the face of that gear. And the face of the gear is going to be, if you would, the width. If we compare it back to a spur gear is straight across. So a horizontal line perpendicular across that face of that gear. Helicals are going to be at a slight angle, okay? Now, a couple reasons. There are some advantages here. Number one, this is a quieter gear set, okay? Because what ends up happening is as we are engaging with the next tooth, part of the previous tooth is still engaged, okay? And that makes it quieter. It's not like one tooth is hitting the other. So it's a quieter gear set compared to a spur gear set. Secondly, because we have that line at an angle, think about Pythagorean's theorem. If we have the angle of a triangle, the hypotenuse, if you would, that's a longer line than just one of the legs, right? Think of the horizontal leg of a triangle with being like a spur gear, but then the hypotenuse being across the face of our gear here on a helical gear. We now have a longer distance that we can distribute the total load that we're transmitting. Now, again, in kinematics, we're not worried about load right now, but for the same size, same face width, we can get higher torques through here, okay, in a more compact design, if you would, okay? So we're distributing that over a longer line because of that, okay? The next one that we have is herringbone. Herringbone, again, is going to be a lower profile tooth. You can see here that, and I know it's not easy to see if you're looking at it on the screen, but in your book, you're going to notice that you have two lines, if you would, coming together here, and the teeth are much smaller. Again, a very quiet type of a gear tooth, low profile gears. And again, we have a lot of surface area or a line contact that we can distribute a load over. The next ones that we see here are going to orient the center lines of the mating gears in 90-degree fashion. So previously in the orientation of the gear sets that we just looked at, these are all what we call parallel gears, meaning that the shaft center lines are parallel to one another, input and output, okay? Down here, when we look at bevel gears, notice that we have a 90-degree orientation of input to output, okay? So that can be a clear advantage or a clear need that you might come across, okay? And then miter gears are similar. They just have a different tooth type of a shape. And then lastly, we have worm gears, okay? A worm gear you're going to notice has a spiraling effect on the input, and then the output is going to be on the gear here. Okay. The advantage of a worm gear is going to be, number one, there's zero backlash. And we'll talk about backlash in a little bit, but that comes into play, especially when you want to accurately or precisely position something. Okay. So many times we'll put worm gears on servo motors. Okay. Things that we want to turn on and off in an automation situation so that we can precisely start and stop things. So worm gears are really good about that. So any questions on kind of the types of gears that we see here? And again, we're going to focus here. Not my hope, but my anticipation for you, like, let's say you would come across helical gears or bevel gears or miter gears or worm gears out in industry. It's not that you won't be prepared for it, but you will have the basics based on spur gears that then you can relate to. Okay. And then with a little bit of, using of vendor catalogs and or other resources that you have, you'll be able to kind of finish up those drives as well. Okay. So types of gears. Let me go back to my PowerPoint presentation and kind of catch us back up. Now, some spur gear terminology. There are a lot of things that we're going to, if you would, maybe vocabulary words that you haven't used or come across very much, up until this point. So some diagrams that we're going to be looking at. So we're going to turn the page and we're going to look at figure 7.4, which is at the bottom of page 262. And we're going to see many of the items that we see here. So I'm going to go underneath there. And the illustration that I'm referring to is right down here at the bottom of the page, okay? What I like about this is nice a close-up view of what we call an involute tooth, okay? That is the standard spur gear tooth profile, if you would, okay? And that involute tooth has the shape that you see here, okay? Now, a couple of things. Let's look at the terminology that we have on here. Number one, we have a pitch diameter. Okay, pitch diameter is going to be denoted by the variable lowercase d. Okay, pitch diameter. Pitch diameter is what we call or sometimes referred to as the effective diameter. It is the point at which all the forces that are generated and the point at which we have tooth engagement with the gear that we're in mesh with. Okay, that's the point. Years ago, when I was out in industry, and it was kind of before we had, 3D parametric CAD that would, if you would, automatically generate the tooth profiles. We would have to draw them, okay? And we will be referring to this in a little bit, but on page 266, here are, if you would, the standard equations to generate all of these items we're going to look at on the tooth profile. So if you wanted, you would have to draw those teeth separately. But what we ended up doing, instead of drawing all those teeth separately, and for a couple of reasons. Number one, time. But number two, we would draw instead, and you may see this on older prints, where you just show the pitch diameter because that's going to be the point at which it would be tangent with the mating tooth, or the mating gear, I'm sorry. If we look a little bit further in the chapter, there's a nice illustration on page 273, where we see two gears enmesh with one another, and we see exactly what I'm talking about, where you show a couple teeth along the perimeter of either and the gear and the pinion, but then this center line circle in both cases is the pitch diameter, okay? And notice that they would be tangent to one another if we would lay them out in a design, okay? So that's the point, or the pitch diameter. That's what we're seeing. Again, the effective diameter where tooth engagement occurs. Now, on this illustration, it kind of looks like it's about halfway in between the highest point, the top of the tooth, and the lowest point, or the root, or the bottom of the tooth. It is not. It is not. Above that pitch diameter is called the addendum. Below the pitch diameter is called the dedendum. Okay, the dedendum will always be deeper or longer or taller than the addendum, okay? Always. And the reason for that is because when the other gear tooth is coming in, that addendum has to fit down in this root. Cannot be the same size because we would have, metal to metal contact, and we wouldn't want that on gears. We want to make sure that there's clearance between the bottom of the tooth and the top of the mating tooth. Okay, so D-dendum's always going to be taller or greater than the addendum as we look at the total height of the tooth and in relationship to the pitch diameter. The pitch diameter is here. The addendum is going to be to the top of the tooth. The D-dendum is going to be the bottom. Now, standard, again, I'm going to refer back to this list on page 266. You're not going to be drawing any of these. You're not going to be calculating any of these because we don't need to nowadays. All right. When we put gears in place in, 3D parametric designs, we just pop in our, diametral pitch, all the information, and it automatically puts it down in place for us. And so you'll notice that here are the equations for the sizes of each one of those. All right. All right, so that's addendum and D-dendum and the pitch diameter. The next thing we want to look at is the face width, okay? The face width is going to be how wide that gear is, okay? How wide that is going to be the distribution of whatever force we're going to be putting through there as it engages with the other gear that it's mating with. So the wider that this tooth is, the wider the face is, the greater the face width, the higher the force that we can actually put through. Okay. The next one that we have here is, I think that's all in that one. There are a couple other ones. You have a tooth width, you've got some radii, fillet radii. They call this the circular pitch. That's just really along that pitch diameter. We're going to be referring to that most often as the pitch diameter. So addendum, D-dendum, face width, pitch diameter. And I think from this one, as far as the way that the teeth look, I think that's about it. Let's go back over here. Addendum, D-dendum. Okay. All right. Now let's look at, over on our next page, let's look at diametral pitch. Okay. So I'm going to start out by looking at diametral pitch, where we look at the top of page 263, figure 10.5. You're going to notice that we see a series of teeth here in each case with a number below it. Okay. It says these are standard tooth sizes, So here we have a 48 and here we have a 3. What do you notice about the numbering system here? What do you notice about the numbering system? The higher the number, the what of the tooth? The smaller the tooth, yes. So the higher the number 48, notice that we have small little teeth. The smaller the number associated with it, the bigger, the chunkier the tooth, okay? The bigger, the chunkier the tooth. So you'll also notice that we go from 3, 4, 5, 6, but we skip 7, we go to 8, skip 9, we go to 10, and so on. Not every number in between is a tooth size, okay? This is referred to as the diametral pitch, or sometimes just said it's a 8-pitch gear. That's what that's all it is. Diametral pitch and pitch diameter sound very similar. Okay, they do. They're very different quantities and they have 2 different variables. So I'm going to remind you back over here, pitch diameter, small d, pitch diameter. This is going to be the physical size of the effective diameter where you get engagement from one gear to a pinion. Okay, that's physically where they size. That's where you transmit the force through and it's where they actually engage. Diametral pitch is the size of the tooth. Diametral pitch is the size of the tooth. Pitch diameter, physical size of the actual pitch circle. Diametral pitch is the size of the tooth. Okay. Now, let's look at the equation for diametral pitch. Equation for diametral pitch. It's right here. The variable for diametral pitch is going to be capital P sub D, diametral pitch. It's going to be equal to capital N, the number of teeth. That would be counting out the outside of a gear, how many teeth are on that gear. divided by that same gear's pitch diameter, okay? Small d, pitch diameter, physical diameter. Capital P sub d, diametral pitch size of the tooth, okay? All right. So we see up here that the larger the diametral pitch number, the smaller the tooth. Now, what does this mean? Let's look at the equation. What this is telling us is how many teeth do we have per inch of pitch diameter? Now, don't get that confused with around the outside, you know, like the outside, the circumference. It's taking the distance across your gear, because that's the pitch diameter. How many teeth can we fit inside of there? Okay. Per unit of length. Okay. So the more teeth that we can fit within a unit of length, the larger the diametral pitch. The fewer the teeth that we can fit, the smaller the diametral pitch. Now, as I said earlier, notice that not every number is on here. We don't see a 7, we don't see a 9, we don't see an 11, we don't see 13, 14, or 15, because those aren't standard diametral pitches. When I have two gears that are in mesh with one another, do you see by looking at this that they have to have the same diametral pitch? I cannot put a number 8 in mesh with a number 10. Can't do it. They're not going to mesh together. They're not going to fit together. Okay. So when we're specifying a set of gears, for instance, number 1, they have to have the same diametral pitch. Absolutely. Okay. All right. Now, the standard diametral pitches that are out there are going to be the ones that you see right here. Okay. So they don't have them all listed above. We hang in industrial design 6, 8, 10, 12. Those are the diametral pitches that we see most often in machinery applications. Okay, kind of standard industrial types of things. And then you can kind of look, you know, to the other ones. You'll notice that some are called coarse pitch and some are called fine pitch. Coarse pitch just means just like a coarse thread, bigger, chunkier teeth, you know, in those applications. Fine pitch is going to be smaller, more dainty, you know, teeth. Okay. Now, over on the right-hand side, we are not going to be covering metric gears, again, for the sake of time, really is all that it is. They have a very similar system, except instead of calling it diametral pitch, they call it modules. That's it. All right. So they have their own numbers. You cannot mix, if you would, English gears with metric gears. Those won't go together because, again, their diametral pitches, their modules are not going to mesh with American gears. Okay. Now, the other item that is important when we have gears meshing is going to be pressure angle. Okay, pressure angle. Let's talk about pressure angle. There are 3 standard pressure angles: 20-degree pressure angle, 25-degree pressure angle, and 14.5. Okay, 3 pressure angles. The 2 that you would make new designs to are going to be 25 and 20. Okay, you do not make new designs to 14.5. 14.5 would only be used when there are existing designs, for instance, out in the field that are incorporating 14.5, that you just have to do a replacement on. Okay, but new designs do not get designed with 14.5. Let's talk about that. Okay, now, as we look at the 2 sets of gears that are coming in, so this would be, if you would, 2 gears that are in mesh. All right. And we're just looking at a close-up of the teeth coming together. Now, as we stated, okay, the pitch diameter for each one of these. So here's the pitch diameter for the upper gear. Here's the pitch diameter for the lower gear. Notice that exactly where those 2 come together, that is where they're going to mesh. Okay. That's where you have contact with one tooth to the next. Okay. This is where, you know, when we, you know, figure out, for instance, what is the layout work that we need, center distance is a big deal, okay? Because we have to figure out how far those are going to be apart so that they appropriately hit at the right spot. Another point here is, as this tooth is coming in, remember the distance from that pitch diameter to the top of the tooth, the addendum is always shorter than the dedendum, and you can see we need this clearance to occur, right? We can't have this grinding at the bottom or the root of the tooth, okay? All right. Now, what you're going to notice is that we have what we call a base circle and a base circle. And as these two come in, do you see how there's a line that's tangent to those two? And if we measure the angle that that line is coming in to the horizontal, that is called the pressure angle, okay? Now, the pressure angle is also going to be the line of action for the force that's going to come in and transmit from one tooth to the next, okay? So, for instance, I want to draw this. I'll do it like this. Okay. And I'm going to do that horizontal. I'm going to do that pressure angle. So this is my point of contact with my tooth. Okay. So this point right here is like that point right there. Now, as I just stated, along that pressure angle, okay, along that pressure angle, we're going to have a resultant force come in. Okay. That force is going to push and going to be the resultant that's going to push from one tooth to the next. Okay. And then as you can imagine, I am going to have a vertical component and a horizontal component, okay, of that tooth. So all of you have had statics, most of you with me, okay, so you remember X and Y components on a resultant force, right? Now, if we have a 20-degree pressure angle, let's say that that's our standard right there. That's the normal. And that is the most popular pressure angle that we would specify. You would specify this as your first go-to because, again, it's the most popular. It's the one that's used, it's going to be the most readily available as well. If we do that, this is going to be what we call our normal force. So we'll just call this F normal, okay? And then we're going to call this one F tangential, and this would be our F resultant, if you would, okay? Okay, 20-degree pressure angle. Now, the other one that we can use is going to be the 25-degree pressure angle. So if I increase that by 5 degrees, what happens? My resultant is going to increase to about this, right? And what happens is you'll notice that my normal has to get longer, right? Component-wise. And my tangential is going to get shorter. Do you see that? Okay. Now let's look at the anatomy of the tooth. Okay, let's look at the anatomy of the tooth. If I am looking at this tooth right here with that same force coming in, and I've got a normal and I've got a tangential. So I've got a normal force here coming down. I've got a tangential pointing this way, and my resultant is coming in. When I hit the side of that tooth, okay, the biggest deal to me is that tangential force. And the tangential force is a big deal because, number one, it's the one that's pushing along the side of that tooth. It's going to be the one that is going to create pitting on that surface, okay? Because that's the force that's hitting in that direction. It is also the force that is going to push my tooth over, which could shear it off, okay? Could shear it off. So when I go from a 20-degree pressure angle to a 25-degree pressure angle, my normal force gets larger, okay? That means that I'm pushing this down towards the center of the tooth where I've got the most material. That's a good thing, okay? And my normal force coming in when I go to a 25-degree gets shorter. So 25-degree applications are going to be for things that are more volatile, things that I'm anticipating that I'm going to be pushing a lot of torque through. So machine tool operations are probably 25-degree pressure angles. Conveyor belts are probably 20s. Okay, depending on what you're moving. If you're moving something in a gravel pit, maybe 25 then, okay? So by going from 20 to 25, like 20 again is that kind of that normal industrial application, and you go to a 25, what you're doing is you're increasing the normal force component so that you're pushing most of that force now, or more force, down into the center of that gear where the material is. Okay, that's good. And you're decreasing the tangential force on that so that you don't have that pitting stress or bending stress for that tooth to be bent over. You will look more deeply at this in machine elements because this is how you size your applications, okay? But I want to give you this background because now let's look at 14.5, okay? 14.5, we would get more shallow still for the same force. See how that would go out like this? And what happens then? My tangential now gets longer and my normal is going to get shorter. So this is 14.5. Do you see how there was probably a lot of issues with pitting of the gear teeth and also shearing off those gear teeth or bending them over? That's why. So we don't do new designs. They are out there. You may come across them, but only in the situation where you are replacing or, you know, servicing something that's out in industry or that's already out in the field. Sorry. Okay. All right. So that's really the difference between the three. Yes.
You said, right, I missed, what is the, like, nice part of having a shallower angle? Is it like more efficient at transmitting into?
I think nothing. There's nothing nice about it.
So why not do all?
Huh?
Why do a 20-degree angle at all and not just everything?
Oh, the 20-degree, why would you do that? Well, you get bigger, taller, chunky, or you get bigger, taller, chunkier teeth. And that's usually reserved for those applications. What's the difference between the two? You know, that's a really good question. I'm not sure why not just do 25 for everything. I'm not exactly sure about that, but normally you move up with the others, the 25 from the 20. I don't know. I never asked that question. Because normally where you'll see 20 and 25s are in the diametral pitches that are like this, the bigger ones. I'll have to look into that. I don't know. It's a great question. Okay. So kind of going back to, if you would, the force analysis, and I know we're not looking at that, but I think it's a good visual for you to understand the difference between the three pressure angles, which is something you need to be aware of in the kinematics world, and why we have the three, and then why the 14.5 becomes something that you really don't want to design to. Okay. All right, so that's pressure angle. Now, the other point about pressure angle is that your gears that are meshing with one another have to have the same pressure angle as well. So they have to have the same diametral pitch and they have to have the same pressure angle. Those are two things that have to be common, okay, between gears that are going to mesh with one another. You can't mesh a 20 and a 25 together at all. Excuse me. I go back to my PowerPoint. So I just want to make sure that terminology, we kind of covered everything. So we had pitch diameter, small d, that's going to be the physical effective diameter around the gear. We talked about addendum, dedendum. We identified where the clearance is between the teeth that come together, between the addendum of one tooth and the dedendum of the other. We talked about diametral pitch, how that's the size of the tooth. Just be careful when you're reading problems, making sure that you've got the pitch diameter and or the diametral pitch lined up correctly with their variable. We just talked about pressure angle. And the only two that I guess we didn't specifically look at, N is the number of teeth. This is capital N is going to be like literally counting the number of teeth around the outside of a gear and or a pinion. That would be the number of teeth. And then the circular pitch, look at the circular pitch. The circular pitch is just, it's going to be a circumferential difference. We'll see here, a distance. So right here is a circular pitch. That's going to be if you would, a distance along the pitch circle from one point on the tooth to the very same point on the adjoining or the next tooth that would be in line. So it's just a little distance there. We don't use that very often, but sometimes it's something that comes up. Okay. Okay. Now, involute tooth profiles, this is going to be the shape of the tooth of a spur gear, and we have seen it in a couple different places. It's going to go to where they're referring to. 9. I missed it. 7, 8, 9. Okay. Okay. They're referring to this profile right here, okay? Now, the profile of that tooth allows for engagement in and out. I have this nice little demonstrator, if you would. I'm going to put it underneath our camera. For those who are in the class, you can kind of play around with this a little bit later. But what this is I've got, looks like a pinion would be on the top. This one will be smaller. This one will be larger. And what you can do is you can move this on their centers. So as we can see, the involute tooth profile allows for one tooth to kind of come in, push back the other, and then engage with the next tooth. So its profile, if you would, has been, you know, kind of optimized in order to allow that motion of in and out as we go from one tooth to the next. Okay. What you also see on here identified is going to be the pitch circle or the pitch diameter. Okay. And then above that pitch diameter is going to be the addendum, dedendum. And then you actually see the pressure angle coming in. If we would measure this along the horizontal, that would be the pressure angle coming in. And that's the line of action of, you know, where the force is, where the, you know, motion is going to be transmitted from one gear tooth to the other. Okay. All right. So I'll have this here so that those who are in the room can kind of play around with that, but that's going to be the tooth profile. Let's look at an example. Okay. Our first example. So this will be our first example for our practice problems. And we are going to look at example 10-1. Okay. 10-1. So, let me go underneath. The problem statement at the top of page 266, okay, we have a 20-degree full depth involute spur gear with 35 teeth, has a diametral pitch of 10. Determine the diameter of the pitch circle. That's the pitch diameter. And then it says the circular pitch and the base circle. We're going to cross off. We're not going to worry about the circular pitch or the base circle. Those would be important if we were manually calculating or drafting, if you would, the tooth profile, but we don't anticipate really ever doing that nowadays, if you would. So we're just gonna calculate the pitch diameter here. Okay. So this is going to be example 10-1. Okay. And per our problem up here, let's kind of identify the items that we are given. Okay, so we've gotten a lot of new terminology. I want to be sure that you're kind of starting to line up the things that we just talked about with the variables that are here in these problems. So it says we have a 20-degree full depth involute spur gear with 35 teeth, has a diametral pitch of 10. So we know that there is a difference between diametral pitch and pitch diameter. Okay. Diametral pitch is going to be a single number that is, it's not unitless, but we're going to see it given to us and we're going to specify it without any units in back of it. So it tells us right here, the diametral pitch is 10. So diametral pitch, capital P sub D, is going to be equal to 10. Zoom out here a little bit. Okay. Again, that's the size of the tooth. And remember, that's not going to be every number. It's going to be 10, 8, 12, 16, those numbers, okay? 20 degrees. 20 degrees is our pressure angle, okay? PA is equal to 20 degrees. Involute spur gear, that just means that we're doing a standard spur gear profile of a tooth. And it says that there are 35 teeth on this gear. So N is equal to 35 teeth. Okay. Determine the diameter of the pitch circle. Okay, so we want to find D. Okay, pitch diameter. Pitch circle, pitch diameter, same thing. Okay, the diameter of the pitch circle is the pitch diameter. Now, we had an equation that related diametral pitch, number of teeth, and pitch diameter. We didn't write it down yet. But if we go a couple pages back on page 263, here is that relationship. Diametral pitch is equal to the number of teeth divided by the pitch diameter. Now, at this point, because there's going to be more equations that we're going to be bringing forth, what I want to do is I want to start an equation sheet. You will be handing in your equation sheet. So I'm going to require you guys to all create an equation sheet. Okay. So we're going to say gear equations. And we're going to add this one to our equation sheet right away. Okay. Because that way, as we move through the chapter, we don't have to be paging around and trying to find what we need. So the first one here is going to be diametral pitch is equal to N divided by D. And I'm going to put the units in back of these, okay? So N on top is number of teeth, right? So that's going to be teeth. And this is pitch diameter, that's going to be inches. So diametral pitch technically has units. And they're teeth per inch. We just don't say it. And we don't specify them like that. I don't know exactly why, but they don't. So when we say a number 10 gear, that's the diametral pitch. And we're not given any units. But when you do your problems, you're going to have to show them because you're going to notice that there's going to be some cancellations and such that are given. Okay. All right. Now over on the left hand or on the right hand side here, we want to say that PD is equal to diametral pitch. And again, its units are teeth per inch, okay? N is equal to number of teeth, and the units are teeth. And then D is going to be equal to the pitch diameter, and the units there are going to be inches, okay? If I know a diametral pitch and I can count the number of teeth on a gear, I can always calculate its pitch diameter. Always. They're all related. All right. So now going back to our problem, this is the equation that we're going to focus on to find what we need here. So in this problem, we are given the diametral pitch. We're given a pressure angle, and we're given a number of teeth. We need to find the pitch diameter. The pressure angle is not going to be used in any equations, actually. No equations. Not until you want to start calculating forces, and that'll be in your machine elements class. Pressure angle is going to be part of that. And for the reasons we just saw when we looked at the normal and tangential force components. So in this case, it's not going to be, but you'll notice that for all of your problems, it's going to be called out because it's the insurance that this is what we're dealing with, okay? And that the pressure angle has to be the same, especially when we have things that are in mesh with one another. So we know that the equation relating diametral pitch to pitch diameter is going to be the diametral pitch is equal to the number of teeth divided by the pitch diameter. So in this case, we want to calculate, or we want to determine what the pitch diameter is. Okay, so let's rearrange this so that we solve for D. So go ahead and rearrange this equation, solving for D. Variable wise. So that means I'm going to multiply D on both sides, and then D will be up here by my diametral pitch. So then my diametral pitch has to be divided on both sides, right? So I'm going to get D is equal to N divided by, or number of teeth divided by the diametral pitch, right? Now I'm going to, this is what I'm solving for, I'm going to put my variables in place. So I know that there are 35 teeth on this gear, and I'm going to divide by the diametral pitch of 10. Now, if I don't put in the actual units for diametral pitch, I am not going to get the right units for diameter, right? Right now, this doesn't have any units in back of it as specified. But you guys know that there's units because from our equation sheet, diametral pitch is actually teeth per inch. We just don't hear it that way and we don't report it that way. Okay, we're never given to us. So we need to put teeth per inch in here. If we don't, you're not going to get the correct units. Right? If I don't put teeth per inch in here, you need to put it in your equations. I'm going to tell you that. I'm going to be looking for that because inches can't magically appear. They're not like radians. They don't magically appear and disappear. Okay. So what ends up happening here is our teeth cancel out top to bottom. Notice that per inch is in the denominator. So if you recall from algebra, it's like multiplying, I say, on top, right? On the numerator. It's kind of like when we divide by 1/2, right? If you take 1 and you divide by 1/2, the ones cancel here and the 2 multiplies on top. Even if you do it on your calculator and you say 1 divided by 1/2, what do you end up getting? 2, right? The units act the same way. So when you're in the denominator of your denominator, they're actually multiplying on top. You guys remember that from algebra? Okay. So that means that our units are in inches here. They're appropriate. If you don't put this in, you'll get points off of your problem and then inches magically appear because you're going to have teeth as your units that didn't cancel. Okay. So you have to put in diametral pitch. Those are units of teeth per inch. And then now we have a pitch diameter. What do we have? 3.5. And that's going to be inches, right? Okay. So as we look at how we formatted this, notice, number 1, I identified my example. Okay. Number 2, identified my knowns. I identified what I had to find. I have my equation in variable form. You have to do this. Has to be there. Okay. And then I want to see your unit, your values with the units. I like to also see you rearrange the equation first, but that's, I think, a personal way of doing problems. So I'm okay if you don't do that, but I always try to isolate my variable that I'm trying to solve for. Then I'm going to put in my numbers with units, canceling out where appropriate and or combining. And then my final answer in a box. This is the deal with the final answer. I'm going to say this again. If my question is asking me, what's the pitch diameter? Your final answer needs to say the pitch diameter is equal to. Now, the standard variable for pitch diameter is D. So I better see D is equal to, in this case, 3.5 inches. Do not just put a box around 3.5 because I don't know what you mean. Answer the question. Pitch diameter is equal to. Okay, I see that a lot. Don't do that. It's like nails on the chalkboard for me. Let me know what you're answering. Like, go back and be like, I know I'm answering for D, but what is D? It's the pitch diameter. All right. So make sure that you put that in there. All right. So any questions on example 10.1? All right. Then your equation sheet, keep that on the side because we will continue to add to that. All right. This is good. It's good. Okay. Standard gears. We've already, I think, alluded to this. This is table 10.3. Yeah, we've looked at this already. So standard gears. So there is an organization called the American Gear Manufacturers Association, and they are the, if you would, the governing body or the overseeing body for gear kinematics gear like profiles and designs and such, and what the standards are. So they have developed these equations for calculating what the addendum is, the D-addendum, the working depth, all those types of things, what the fillets are going to be based on, you'll notice, the diametral pitch. Okay. So the size of the tooth that's identified is the basis of that. Okay. Now, as we look at, and this is a good reminder as well, when we look at the standard diametral pitches, if I would go to a gear manufacturer like Falk gear or Browning gear or Rush gears, those are all, kind of standard industrial types of gearing, they are going to have, these diametral pitches available probably only, because those are the standards, okay? And all of their gears are going to be based on those. So many companies, more than none, some companies do some manufacturing of gears in-house. If you happen to be a transmission builder, for instance, you'll probably make your own gears in-house because it's just economical for you to do so. But if you're not creating gears a whole lot, but you're incorporating them into some of your designs, you're going to go out and you're going to purchase gears. So in our book, we have charts here that we're going to be working with for the examples when we choose gears. But I'm going to emphasize to you that these are going to be based on the manufacturer's catalog that you're ordering from. So you're going to be going there, and whatever they have, going on is what you're going to be able to, have available to you. So vendors and where you can get them and how you can get them are going to be based on that standard diametral pitch. A gear manufacturer is not going to do a diametral pitch of 7. They're not. They're going to do a 6, an 8, a 10, and so on. Okay. And again, those standards for sizes and available diametral pitches and such are going to be the decision of the American Gear Manufacturing Association. Relationships of gears and mesh. So let's start looking at center distance, okay? As a designer, you will be responsible for layout work and making sure that things are going to, have enough room, but also fit together. And when we're talking about gears being in mesh, center distance is a big deal because that's going to set up where we're going to, mount things. So let's look at center distance. And this is at the top of page 268. And we have 2 equations here that would be available to us to calculate center distance. Okay. Now we're going to be looking only at external gears. So we're going to use these 2 equations right here. So at the top of page 268, okay, equation 7 or 10.7 and 10.8. Okay. Now we can calculate the center distance by just taking the radius of each one of the gears that we're looking at in mesh and just finding the radiuses and adding those 2 together. That's the distance between the center. I'm going to go to an illustration here. So on page 273, we kind of briefly looked at this, and you don't have to go there if you don't want to, but center distance is simply going to be when I have 2 gears in mesh with one another, what is the distance between the center of one to the center of the next? Okay, so what is that distance, capital C here? That's the center distance. That's what we're looking at. So when we know the pitch diameter for each of those gears, if we just divide each one of those in half and add them together, that's the radius of one plus the radius of the other. That's going to be one way that we can get center distance. So that's what they're identifying in that first equation. Okay. The second way that we can get at it is we know the pitch diameter of each of them. Okay. We can say, all right, the pitch diameter of one plus the pitch diameter of the second, just divide it by 2, and that's the center distance. Yeah. Now, if we substitute for the pitch diameter, number of teeth divided by diametral pitch, we can rearrange and we can get the center distance by using the number of teeth in one plus the number of teeth in the second gear. So the first gear, second gear, so pinion gear, divided by 2 times the diametral pitch. Okay. So what I want you to do is add these 2 equations to our equation sheet here so that we have that available as well. Because again, you don't want to be paging through. So center distance is going to be equal to R1 plus R2 equal to D1 plus D2 divided by 2. Or center distance can be equal to N1 plus N2 divided by 2 times the diametral pitch. Now, the only variable we need to add here that we didn't have earlier is the radius. So I just put R is equal to radius of the pitch diameter, and its units would be in inches. Okay. I'm not going to put that radius is equal to diameter divided by 2 because I think we all know that. Okay. So if we look at our next slide, you're going to notice here, we're going to look at another example. Okay. Our next example is going to be 10.3. It's just below those two equations on that page. And here we are. Okay. So we have a cement mixer and it says we've got two 5-pitch. This is that diametral pitch. So I have it identified as P sub D is going to be our diametral pitch, 20-degree full depth gears are used on a small construction site concrete mixer. The gears transmit power from a small engine, which is right here, to the mixing drum. Okay. And they do that through our pinion, which is the smaller of the two gears that are in mesh, to the gear that's then attached to the mixing drum. The pinion has 15 teeth and the gear has 30. So again, pinion is always going to be the smaller of the two that are in mesh with one another. So that means that this one with the 15 teeth is going to be denoted as number 1 or the pinion. And then 2 is going to be the gear. Okay. And then we want to calculate the center distance. So for our problem, example 10.3 here, we want to identify our knowns and then what we're going to solve for. So example 10.3. Okay. So you kind of can see what I already have identified here. So our diametral pitch is going to be equal to 5. So another way that we hear it called out is a 5-pitch gear. That does not mean it's 5 inches in pitch diameter. It's a diametral pitch of 5. Notice there's no units in back of 5. Okay, no units in back of 5. So that's our diametral pitch. We know that the number of teeth on our pinion, which is going to be number 1, is 15 teeth. Okay. The number of teeth on our gear is 30 teeth. That's all we're given. We want to find then C. Okay. We want to find the center distance. So we want to find the center distance. We'll go back to our equations here and we've got a couple options. And as we look at what we're given, the second one seems to be the one that's going to make sense for us, right? We know number of teeth here that are given and we know diametral pitch. So go ahead and calculate the center distance. Make sure you put units in for everything so that you get inches for center distance. Oh, I need to add that to my equation sheet. I didn't put C. C is equal to center distance. That's the variable. If you didn't add that now. And that's going to be units of inches all the time as well. C is center distance. I was looking at the variables in each equation and making sure I had those covered. So go ahead and put your numbers in the way you think. Put the units in place. And see if you can get units of inches for center distance, because that's what we'd be looking for. So let's look at putting these values in. So I know it's going to be N1 plus N2 divided by 2 times the diametral pitch. So the number of teeth in each. So I've got my number of teeth on my pinion is 15 teeth. So I'm going to put 15 teeth in back of that plus 30 teeth. Okay, always with units, and teeth are units. Okay, divided by 2 times 5. Because 5, I didn't have any units up here, right? Tyler says, nope, you do have units. They just don't say them, right? What are my units? Should I add here? Because otherwise, right now, only teeth remain, right? And my center distance is not called out in teeth. It's called out in inches, right? So what are my units here for my diametral pitch? If you need to, you can look back here. We did add them to our equation sheet. It's teeth per inch, right? Yep. So this is going to be teeth per inch. So now, when these two combine on top, they don't multiply to be teeth squared. They're just going to be teeth, right? So it's going to be 45 teeth. So my teeth are going to cancel on top with this one. And inches, again, is in the denominator of the denominator. So it's actually multiplied on top. So inches are what we're left with, which is exactly what we're expecting for center distance. This is why we put our units in all phases of the problem, because when we cancel and or combine and we end up with units that we know are correct for that quantity, then there's a good chance that we set it up correctly, which is 95% of the problem, right? Okay, so if we take 45, we divide by 2, we divide by 5, I think you're going to get 4.5. And that's going to be inches, right? So C is equal to 4.5 inches. Notice again, you're answering the question. The question was determine what the center distance is. So don't just put 4.5. C is equal to, we're answering the question. Center distance is equal to 4.5 inches. And make sure you have your units, and then I can see that the units in this case of inches weren't crossed out. They were left over. Okay, questions on example 4 or 10.3. All right, these are fun, aren't they? Okay. Velocity ratios. Okay. Actually, this is probably a good place to, let's just take a break. I've been talking for about an hour. It's probably a good chance for you to kind of get up and walk around a little bit. So it's 11:12 right now. So if I give you 15 minutes, that would be 27, if you guys can come back. Okay. So I'm going to stop the recording or pause it. Okay, so we're going to continue on in our PowerPoint, and we are going to be now going to section 10.7, which is spur gear kinematics. Now, the two items that we have on this slide are velocity ratio, capital V, capital R, and pitch line speed. Sometimes it's referred to as V sub P or V sub T. I think in the book here it's V sub T. I think they might have changed it, and but you might see it sometimes as a straight line velocity of the pitch circle or the pitch line. So let's talk about these two items. First of all, the velocity ratio, capital V, capital R. When we have two gears that are in engagement, we want to determine what is the gear ratio between them, or what's the ratio that's being accomplished. And that's probably the way that you normally hear it said. So it's specifically called velocity ratio, and we're dealing with just one set of gears. So one pinion, one gear. What is the ratio between them? So for instance, if we look at the angular speed of the driver divided by the angular speed of the driven. So when we talk about driver driven, driver is going to be like the input. So most often the driver in most applications for gears is going to be where we want to slow that down. So that is going to be the higher value. So for instance, a motor, 1750 RPMs, 900 RPMs, 1100 RPMs. That's going to be the angular speed of the driver. The driven is going to be what it's in engagement with. So like on the last example we looked at, it was the cement mixer. Okay. All right. So we want to know what is the ratio between those two speeds. So sometimes, we might say it's a 2-to-1 ratio. That means that the faster moving driver has to go around 2 times before the driven is going to go around once. Okay. So if we actually, I'm going to bring up that cement mixer that we looked at just a little bit earlier. So I think this is important as far as just perspective. When we have two gears that are engagement with one another, pinion and a gear, the ratio would be, how many times does this pinion have to go around to get this one to go once? Okay, that's what the ratio is all about. Okay. And that's why many times our faster one is going to be on our pinion, and our slower one is going to be on our gear or output. Okay. Doesn't have to be that way, but that's a lot of the percentage or the majority of the applications. Okay. Now we see this play out in the illustration on page 273, which is at the start of this section 10.7, where we see a gear engaged with a pinion. This would be, if you would, your input, okay? Or the driver. The driver, okay? That's going to be your input. Your output is going to be the driven. Okay, driven. And again, many times it's going to be the larger of the two because most often we're trying to reduce the speed. So you can imagine this is going faster, but because of the perimeter of this one being larger or more teeth that it has to engage with, this isn't going to go around as fast. It's not going to go around as fast. It's going to slow down. And a lot of times we want to know what that ratio is. So if I have 20 teeth on my pinion and I count and there's 60 teeth on my gear. Any guesses as to how many times my pinion has to go around before I get one rotation on my gear? Just put a number up, like with your hands. I'm seeing the number 3, 3, 3. Absolutely. And that is the relationship we see a lot. Now, it doesn't have to be an even number because sometimes they're not. You might have 15 teeth over here and 85 teeth. Oh, I'm probably picking bad numbers. 22 teeth over here. I don't know, whatever it is. But it doesn't have to be it doesn't have to be an even number, meaning it doesn't have to be an integer number. It might be 2.5. It might be 2.8. It might be 2.2. Okay. But we just want to know how many times does it take for this to go around to get this one to go one time, okay? So through our velocity ratio, that's what we're looking at. That's exactly what we're looking at. And we can calculate velocity ratio in a number of ways depending the information that we have. And that equation is right here. Velocity ratio, capital V, capital R, is going to be equal to W1 over W2. Remember, our ones are our pinions. Or it's going to be R2 over R1 radiuses, or it's going to be D2s over D1s, or it's going to be N2s over N1s. You want to add this. I love that you guys already started adding that to your equation sheet, okay? I'll add mine on the side here while you guys do. Now, if I'm physically out in the field, the one that's the easiest to get at is the number of teeth. I can literally just count the teeth. I don't have to try to figure out what is the pitch diameter. I'll have to try to figure out how fast it's going around. You can count the teeth on one, count the teeth on the other, divide the larger by the smaller, and you've got your velocity ratio. That's all. Okay. So as we look here, I did write mine underneath here. What are the units for velocity ratio? What do you think? Nothing. It's unitless, right? Because if we look at this, this is going to be RPMs to RPMs, cancel, cancel, right? Inches to inches, cancel, cancel, teeth to teeth, cancel, cancel. So they are unitless. So velocity ratio is just that. It's a ratio to give us information about how many times our driver has to go around in order to get that driven to go around once. So in the case of the 20 to 60, it only goes, it's going to go around 3 times to get that other one to go around once. Okay. Now, the other equation here is that straight line velocity. How does that work? So let's go back a page to 273. Go back to this illustration right here. Whichever one we look at, the pinion or the gear, okay? If we wanted to represent this with a standard kinematic diagram, we would show I'm going to do the gear because I've got more room here. We would show the center or the center of rotation or where we have our gear mounted. That's going to be our frame. Okay. And this is going in a counterclockwise direction. We see W2 is going in a counterclockwise direction. And then if we take a line and we go all the way to our pitch diameter, do you see how that's like a link? You see that? That would be like link number 2, right? Other ways, we saw this, illustrated this way when we had circular features that were like flywheels, right? Okay. And then if we know that this is rotating at a counterclockwise direction, then the straight line velocity component of that endpoint that would be at the pitch diameter, right? Radius, that is going to be directed straight down. That's the straight line, right? Because it's perpendicular back to its radius of rotation. Does that look familiar? Yes, right? We've been doing this in our 4-bar mechanisms. But in this case, we're looking at, if you would, one gear and its relationship between its angular velocity, its rotational velocity to the straight line velocity of that point out at the pitch diameter. Okay. So that's going to be another equation that we have. So up here at the very top, we call that pitch line speed. Okay. How fast is that moving in a straight line along that pitch line? So we want to add that to our equation sheet. So we'll use VT instead of VP. So VT is going to be equal to R. We're just going to put R times W because it's going to be on whatever, if it's a gear or a pinion. Okay. Now that radius is still going to be the radius of the gear and the angular velocity. So VT is going to be pitch line speed. And it's going to have units of inches per second. Okay. We also called this the straight line velocity component of, but when we're talking about gears, that straight line velocity is on the pitch diameter. That's why they call it pitch line speed. Okay. That's going to be in inches per second. That's a straight line velocity. Our angular velocity is going to be given in RPMs, right? But doesn't this equation look familiar? In and out of this equation, what does it have to be? It has to be radians per second. So we're going to be given it in RPMs, but we are going to always have to convert between radians per second because if we get it out of that equation, it's going to be in radians per second, or if we use it in the equation, we have to convert it to radians per second. But we'll always report out or get it as RPMs, just like we were earlier in our modules. Okay. All right. So good. Do you kind of start seeing those relationships from things that we've been doing, right? Especially when we start showing, I think, the kinematic representation of, right? Okay. Then let's do an example. Okay. The example we're going to look at here is going to be a set of gears is used to reduce the speed of an electric motor to a shaft driving a grocery checkout conveyor. The gear on the motor shaft, okay, so down here, is a 10 pitch, has 15 teeth, and drives at 1800 RPMs clockwise. Determine the speed of the mating gear, which is 45 teeth, okay? Also calculate the pitch line speed. So what I want you to do is, in that example, I want you to go through and identify all the variables that you know, okay? And then we'll look at it together. See if you can figure out which are the ends, which are the diametral pitches, which are the pitch diameters, if there's any, which are W's or V's, okay? So just kind of read through that and see if you can identify what you're given in the problem based on the statement. All right. So as we look here, it says we have a set of gears to reduce the speed of an electric motor. All right. The gear on the motor shaft is a 10 pitch pinion. What would 10 pitch be? What variable would that be? PD, diametral pitch, exactly. So this is going to be your diametral pitch, right? I'm going to write that down on mine. So it's 10. What is, it says it has 15 teeth. That's going to be what? What variable is teeth? Yep, this is going to be N, and it's going to be number 1 because it's telling us that this is the pinion, right? Yep, so N1 is equal to 15 teeth. Good. And it drives at 1800 RPM. What variable is 1800 RPM? W, yep, and that's that little w, right? Angular velocity. So 1800 RPMs. Good. So this is going to be W, and it'll be of the pinion, so W1. And it wants us to find the speed of the mating gear. So what variable would that be? W2, right. So we want to find W2. And it says, which has 45 teeth. So what variable would that be? That would be N2, exactly. That's going to be N2. Because that's of our gear, it's the larger one. And it also calculates the pitch line velocity. What's that variable? VT, exactly, VT. Okay. So I kind of wrote it out as we went. So our knowns are over here on the left-hand side. We know our diametral pitch. We know the number of teeth on the pinion and the gear. And we know what the rotational speed of our pinion is, or the input right off that motor. And we want to find what is the angular velocity or the rotational speed of the gear that it's meshed with, okay? Which is going to be this, which is going to be the roller on our conveyor, right? Okay, so that's going to be going at the same speed because they're in the same center or in the same shaft. And then we want to know what the pitch line speed is, okay? Now, just as a note, pitch line speed, it didn't ask for it to be on the pinion or the gear because the pitch line speed is going to be the exact same for both of these because they're engaged. Does that make sense to everybody? This same pitch line speed would be on the pinion as well, okay? It's just that the pinion is going to be rotating faster to obtain that, okay? The radius is going to be shorter. So pitch line speed, whether we want to know it for the pinion or the gear, the pitch line speed is the same because that's the point of engagement where they're going to rotate. All right. So if we want to find W2 and VT, this is what we got. So if we look on the top here, the things that are up here, for the most part, are distances, right? We want to find rotational speed, okay? So we're probably going to focus down here. That's where we see some W's, right? So as we look, what are you thinking? What do we know? We know number of teeth in each, right? So we can say we know N1, we know N2, okay? What else do we know? We know diametral pitch, right? We know diametral pitch, good. So if we know diametral pitch, we actually could go up here and we could calculate pitch diameters for some things, right? So we technically could get there, right? So we could probably get these if we wanted to. But we have to calculate them, right? Do we know any W's? Yes, we know W1. And what are we trying to find? W2, right? So since these are all equal to each other, we could set, I don't know if I can do this. We could set W1 over W2 equal to W2 over N2. Do you see that? And we would know 3 of the 4 variables to solve for W2. Agreed? Okay. Go ahead and do that. Set that up in this ratio form because It's saying that these are all equal quantities. Make sure that you always have the right variables on the top and the bottom. It always has to be the larger variable on the top. That's why W1 is on top for the angular velocity, because it's going faster than W2. But then as we work, through the other ones, physical size, the gear is going to be larger than the pinion. Okay. So what I started doing here is I started my ratio, W1 over W2 is equal to N2 over N1. And then what I did was I rearranged so that I would solve for W2, because that's what I'm trying to find in the first part of this problem, okay? So that means I'm going to take W2, I'm going to multiply it up on the other side with N2, and then I'm going to put N1 up on the other side, and then N2 has to come down. So kind of some algebra rearrangement there. Any questions about that, though? The rearrangement. Did you guys get the same thing? Hopefully. So now solving for W2, I'm going to put in my 1800 RPMs. And I'm going to multiply that by 15 teeth. And I'm going to divide by 45 teeth. The teeth cancel out and I'm left with RPMs, which is good because that would be an angular velocity. So my W2, what do you guys get for your value? 600. I'm not gonna, is it? Gosh, I did that in my head. 600 RPMs. So that's the first part of this problem. What is the angular velocity, or the W2 of our gear? How fast is that rotating? Okay. So our input is going 1800 and our output is going 600. Now the problem didn't ask us for this, but let's go ahead and calculate our velocity ratio. Okay, meaning what is the ratio of how many times does that input have to rotate in order for the output or the gear to rotate around once. So I'm gonna go to my other side here. So velocity ratio, piece of paper. Velocity ratio we know is going to be equal to W1 over W2. We now know W2, right? So we can say the velocity ratio is equal to W1 over W2. I know W1, which was my input, was 1800 RPMs. And I know I just calculated my output to be 600 RPMs. So the RPMs cancel, and my velocity ratio is 1800 divided by 600 is 3. Again, the problem's not asking for that, but I wanted to kind of bring that back. And that tells me that my pinion off of that motor has to go around 3 times in order to get the gear, which is rotated to the, which is connected to the conveyor, is only going to go around once. So a 3-to-1 ratio. Okay. Back to the problem. The other part of this problem is they want to know what the pitch line speed is at that engagement point of the 2 gears. Okay. So our pitch line speed is going to be the radius of rotation multiplied by the angular velocity. But remember, we're inside of this VT is equal to RW. We have to have W reported or used in radians per second. Okay. Now, the information that we're given in the problem is diametral pitch we know is going to be common between the two. And we're given the number of teeth for each. So we look here, we have to know the radius of one of those gears, right? So I'm gonna go back to that one illustration. Okay, so we want to find the velocity ratio. So if I tip this up here, this is the orientation of the two that we have. Okay, and what I want to do is taking the radius of one of those gears, pinion or gear, doesn't matter. I want to know what is this pitch line velocity. That's what I want to calculate. Okay, so the information that we're given, number of teeth, diametral pitch, and W. Can we calculate a radius using that information? We can calculate a diameter, knowing diametral pitch and number of teeth, right? All we have to do is we have to pick, are we going to use the pinion or are we going to use the gear? Now, we always also want to think about what is the least amount of calculated information that we have. So for instance, we want to use as much given as possible, right? So if we look back at our problem, we know the diametral pitch that's given. We know the number of teeth on the pinion and the gear, right? But we also know the rotational speed of the pinion. Even though we calculated the rotational speed of the gear, this one was given information. So there's, I don't think we did this one wrong. Actually, I'm certain we didn't. You could use either one, but it's always good to use it. So what we'll do is we'll use the information from the pinion to find the pitch diameter and then use its radius, half of that, in the equation to do the pitch line speed. Okay, so let's go ahead and calculate the pitch diameter of our pinion. So D1 is going to be equal to, so I know you guys can probably do this algebra. So since D is in the bottom of our equation, we would multiply it up and then the diametral pitch would have to come down underneath, right? For algebra, you see that? So D is going to be equal to, let's see, the number of teeth divided by the diametral pitch. So that would be the number of teeth in our pinion divided by the diametral pitch. Diametral pitches for the pinion and the gear, they're the same. So the number of teeth on our pinion is 15 teeth. Okay. And the diametral pitch, as it stated, was 10. Now, don't forget, you have to put the units of teeth per inch here in the diametral pitch. Otherwise, you aren't going to get the appropriate units of inches for pitch diameter. So my pitch diameter of my pinion is going to be, it looks like 1.5 inches. Okay. Now, the radius then is going to be D1 divided by 2, which is going to be 1.5 inches divided by 2, which is going to be 0.75 inches, is equal to our radius number 1, right, that we need. I really shouldn't put a box around that. That's not a final answer. I'm sorry. We'll use it. Maybe we'll put a little wavy underneath it. We need that radius. Okay. Now, what we are trying to find is the straight line velocity or the pitch line speed. Straight line velocity and pitch line speed are the same thing. It's going to be equal to, as we said earlier, the radius number 1 multiplied by the angular velocity number 1. So we know that radius number 1 is going to be 0.75. But we also know in and out of this equation, we can't put RPMs is what we have. So remember, W1 is 1800 RPMs. We need to convert that first to radians per second. Okay. So over on the side here, I have 1800 revolutions per minute. Make sure you expand this out. Don't put RPMs on top. It says revolutions on top per minute. Okay. I've seen it a couple times where it's RPMs on the top, RPMs on top, and then you have minutes underneath. No. It's revolutions on top. We're expanding out revolutions per minute. Revolutions on top, minutes on the bottom. And then it's going to be 1 revolution is 2 pi radians. Okay. Revolutions cancel. I'm in radians per minute, and then I have to get 1 minute is equal to 60 seconds. So minutes cancel. Make sure you cancel the units as well. Sometimes I see you guys write this out and there's no cancellation. So how do you know? You're just like magically appearing it again. Don't do that. So my W1, what is it in radians per second? What's my number? 188.5. Anybody else get that same value? Anybody else get that same?
I figured it out a little.
Liam got it too? Okay, awesome. All right, now this is the value that we're going to be putting up there. So our straight line velocity is going to be equal to 0.75 inches times, I'll give myself enough room, 188.5. That's why I use pencil. Radians per second. So this is going to go up there. There we go. So my straight line velocity, what's my number?
41.
141.5. And what are my units? Inches per second. Okay. This is a final answer. This is a final answer. So the two answers that they were looking for is, what was the rotational speed of our gear? 600 RPMs, right? We got that. So make sure you label it W2 is equal to, box around it. And then our other final answer, we did an intermittent little calculations of velocity ratio. Then our other final answer is the straight line velocity is 141.5 inches per second. Okay. Inches per second. All right. So if I remember correctly, I believe that is as far as I wanted to go today. Okay. So we did example 10.8. We're going to stop here today. There is a little bit more in this session, but I'm going to save it for the next time because it kind of goes along with the second part. So, but before I let you guys go, let's take a peek at your homework assignment, because what we've done today, there is a significant amount of the homework that you can already start working on. So let's look at assignment number 4. And in the back, the items that you are able to do is everything through and including 1016. Okay, so let's take a peek at the end of the chapter at each one of these so that you know what it's asking for. And again, the things that we got through today will give you the ability to complete those problems. So between now and the next time, you can actually start making progress on this. So I'm going to go back underneath. So on page 295, okay, is where the end of the chapter problems start. And if I remember correctly, I want you to do just part A for numbers 10, 5, and 10, 6. So I'm going to go back underneath. So part A says for questions or for problems 10-1 through 10-4. Oh no, down here, sorry, because you're doing 5 and 6. For problems 10-5 through 10-8, we're just going to do the center distance, okay? And the two that you have here are 10-5 and 10-6. So for instance, for number 10, it says 2 12-pitch, 20-degree, full-depth involute spur gears are used in industrial circular saw for cutting timber. The pinion has 18 teeth and the gear has 42 teeth. You just want to calculate the center distance. Okay. Same thing for number 6. Okay. For number 9, I want you to make this change here. 2 mating 12-pitch gears have 18 external and 48 external teeth respectively. Do not do the internal. Okay. So external teeth on both. So those are the standard equations that we were looking at. What you want to do is you want to calculate their pitch diameters and their center distances. So 2 things for number 9. Okay. Now you're going to look at 13 and 14, very same thing. No internal gears. You're only going to do external gears. So that means that you want to find the pitch diameter and the center distance for an 8-pitch, 18-tooth pinion mates with an external gear of 64 teeth. And then number 14, a 10-pitch, 24-tooth mates with an external gear, 108 teeth, pitch diameter and center distance. If you calculate the internal, We didn't go over that. So that's your clue that you probably don't have to do that. Okay. And I'm telling you right now, just external teeth. Okay. So you won't get credit for it, even if it's right. All right. And then the last two that you can do are 15 and 16. And it says here that you want to find the speed of the gear. So that's going to be W, and the pitch line velocity, which is going to be your VT for number 15, 8 pitch, 18 tooth pinion rotates clockwise at 1150 RPM and mates with a 64 tooth gear. And then same type of information. So you want W and VT for each of those. Okay. Any questions at all for right now? So you can get through, a bunch of problems. Yes.
Oh, we're not doing any CAD work.
There's no CAD work for this one. Yes. Are you happy about that? No, just calculations here. Yeah, just calculations. But when you do your calculations, make sure that you do it in the format that I'm always asking for. Always show me your equation in variable form. Show your values for each one of the variables, including units in all phases of the problem, cancel and combine as needed, and then put a box around your final answer with the correct units. I don't want correct units magically appearing, okay? And the best question you can ever ask me is, how do we resolve the units for that? How do I get the right units for that? I'm not getting the right units. I will all day stop whatever I'm doing. Let's figure it out, okay? Because that is your key. I can't emphasize that enough. That's your key to knowing that you set it up correctly when you get the right units. Okay. And that's why I make you guys do that. Right. It is so valuable. And especially when you have mixed units in a problem. Sometimes we've seen problems where part of the problems is in feet per minute, another part is in inches per second. And now if you just put variables in and you don't check your units, you're not going to get the right answer. End of story. Okay. But if you pay attention to those units and see if you can cancel, you're going to notice I can't cancel the feet with the inches. I have to do some conversions here. Okay. Or if you start putting RPM in error in a question, you're going to be like, well, how are these revolutions per minute combining with the inches? That's not right. I need to get something, you'll start to see that there's a problem. And then you can back up and troubleshoot it without having to get it wrong. Does that make sense to everybody? Okay. So I know it takes more time. I know you have to write it out. I know, but it's not about speed here. You want to make sure that you understand and especially set up things correctly. And units are a huge help in that. All right. So that's where I'm going to end today. So again, you have a significant amount of the problems here that you can work on. The next time we get together, we'll finish up the units or the module, and then you'll be able to then finish up these last 4 problems that you see here. As we look at our practice problems, it's worth kind of looking back over there. We've done some of these as well. I think we did the first 3 maybe. Okay, so we have the next ones that we're going to be finishing up the next time that we get together. Okay, your questions here, don't forget to answer the questions. Sometimes people are forgetting these. I will start marking 0 out of 10 if you forget them. I don't want to do that. So make sure that you're completing these sentences. 2 things you learned in Module 4, but I mixed it up a little bit. For this one, I'm asking you to name or describe 3 places that you see applications of gears in your everyday life. All right. So add those somewhere on your practice problems when you hand it. Okay. So there aren't any questions, then I'm going to stop the recording and let you guys work.